Okay, we're going to take a look at working with exponentiation as an encryption device. So we looked at before addition and multiplication in a previous module. Now we're going to take a look at exponentiation. We're going to, little Fermat is going to be really crucial here, so we're gonna go through it and do this. So remember last video I mentioned like we have to be really careful about using calculators because when we start taking values to these exceptionally high powers, it doesn't, the calculators aren't gonna work well. So so Wolfram Alpha is a good one to use, and so that's what I've got set up over here. It's we don't need a lot of, we don't need to sign up for anything. It'll do the basic work that we need to do here. So the first thing, same plain text as we did before, so to be or not to be. We'll put a little dash at the end here, so this is the same thing as we did last time, just took its placement in the alphabet and combined them into 3 and 4 digit numbers, although remember this is still 0205 or 0527, so we could still think of it. So what we need to do next is we need to pick a mod that is prime. So I have 4409 here. Do I know it's prime? Well, the easiest way probably to do this is to just go ahead and I can use Wolfram Alpha to actually ask it, is prime 4409? And I type that in, and for some reason it changes is prime to sprite. Don't ask me why. I must be thirsty. Is prime. There we go. And it says, is 4409 a prime number? Oh, yeah, it is a prime number. Great. Okay. You could just pick a random prime and try, or random number and try that. Of course, obviously, you could keep picking composite numbers. So another way to do this is you could just say, use the command prime, and just pick like what prime do you want. So I'm going to say 550. Okay, so this is the what it'll do is it'll return the 550th prime number. So I hit enter, I wait patiently while it sends it out. Calculate it, result 3989. Okay, so just remember when we're in this particular cipher, you want to have a mod that's at least probably 27 times 27 or 27 times 8, just to make sure it's big enough to deal with any of the numbers that could come up when you're working here. It's got to be over 3,000. Okay. So anyway, so that's helpful to remember. The next thing I need is I need a key, and it needs to be relatively prime, not to 4409, but to 4408, because if you remember little Fermat, that's remember what happens when we do that on here. If we do 17 to 4408 mod 4409, we get 1. Okay. Now, it's worth mentioning really quickly here what's going on. So Wolfram Alpha, like if we were to do this by hand, well, to talk about what your calculator does. So what your calculator does with the 17 times 4408, like if you were to actually put this in your calculator, assuming it would work, which, to be honest, very few calculators out there will actually calculate that. But let's say it does. What it's going to do is it's basically turning into a floating point number, and what's going to happen is it's going to do a bunch of rounding and turn it into a scientific notation problem, which means essentially it's only holding on to maybe the first 15 digits, possibly 20 digits, and then the rest of it's going to be all zeros. So because it just drops those, because it figures, this person doesn't really want that. And then your calculator afterwards, so your calculator would do that first and then try to apply the mod to that, and it's just going to give you a completely worthless answer. Wolfram Alpha doesn't do that. It knows I'm in the world of mods, and so it knows how to do that correctly in the background. Because it's programmed with all of these things, and it's done correctly. If you end up writing a program for RSA, you're going to have to really be thinking about how to do this in the programming language, because you have to take into account that these numbers, if you just tell the program 17 to the 4408, and then you're going to take a mod of that, I can almost guarantee you, if you're not really careful about how you do that, it's going to backfire on you. So you're going to really have to think about that if you do end up doing the optional programming assignment. Okay, so we know that 17. Oh, we need to make sure that 17 is relatively prime to 4408. It's just not enough to do this, but let's just make sure. So one way we could do that is we could just do GCD of 17 and 4408. And what do we get? Awesome. Result is 1. Okay. The other way I could do it too is I could say factor 4408. And actually it showed up before I even did anything. 2 to the third times 19 times 29. None of those is 17, so I'm good. Okay. So basically we've got our stuff set up. Here's our mod. Here's our 17. And here's our key. So how are we going to go ahead and find this number right here, the cipher number? Well, we're going to take the original plain number, 2015, and raise it to the 17th power mod 4409. Okay. So I'm going to come up here and again using Wolfram Alpha. I'm not going to use the background in the spreadsheet, that mod thing, and I'm going to get 2015 to the 17th mod. Looks like somebody did it in a different mod. 4409. Let's do it in the background, and I'm going to go ahead and put 570 here. Okay. And let's do the next one, 205. So that's easy because I can just delete the 1. So 205 to the 17th, mod 4409, and I get 544. So not quite as automatic as what we did before and working with a spreadsheet, but we just can't trust what's going on in the background over here. I'll just do a couple more, 1518 to the 17th. And that's going to be 120, and I'll just do one more. And then you should have the idea by now. So 1415. And that's 891. Okay, so you can do the rest on your own if you want to try that out. So now we have to figure out the decryption key. So how do we get the decryption key? Well, this is where the 4408 comes in, because using little Fermat's, basically what we want to find is the multiplicative inverse for 17 in 4408. Okay, so we could make a table and we could look at all of those values. So what times 17 in 4408 equals 1? We could use Euclidean algorithm to calculate that. Or we can use the fact that what we're trying to find is the inverse. So what I can do instead is say 17 to the negative 1. Now notice the first thing it says is, hey, that's 1/17th, but that's because it's not living in the mod world yet. So we're going to do mod 4408. And we get 2593. Okay, so again, it knows we're in the mod world, so it gives us this number back again. So that's our decrypt number. Okay, so how do we use this to check to make sure that our 570 was the right number and we get 2015 back again? Basically what we do is we now take the 570, raise it to the 2593 in mod 4409. So we have to be a little careful because we're bouncing back and forth between the 4408 and the 4409, but really the 4408 is just there to get us the 2593. Okay, so watch what happens. If I do 570 to the 2593, and I do that in mod 4409, I get 2015 back again, which is what I expected. And again, I'll check one more time. So I'm going to try 544 now. And hopefully I'll get my 205 back. And there's my 205. Okay, why not? One more, just to make sure. Plug in my 120, hit enter, and there's my 1518. Okay. So just be careful. The only time the 4408 really comes into play, I mean, we need to make sure it's relatively prime to 17, so little Fermat works, and it's to get our decrypt key. But when we're going from the plain text number to the cipher number, and from the cipher number back again, we're using mod 4409. So just remember that. Okay, so try a few of those out, see how it works. You'll need that for your pair work. But definitely pull up Wolfram Alpha as well. Okay.